Welcome to Calculus. Today we will investigate how to analyze logistic functions and logistic differential equations. We'll take a look at two examples, one of each. Our first example is going to start with the logistic function P of t equals 2,100 divided by 1 plus 29e to the power of negative 0.75t. We want to analyze this logistic function for really four items. I want to find the k value, which if you recall for a logistic function is the growth rate. I also want to find the carrying capacity, which is often called the a value in a logistic function, the initial population. So that we'll need to consider, that's when time equals 0. And then the time when the population is at 50% carrying capacity. So let's begin. To help ourselves out, we want to give really the template that we traditionally use for a logistic function. So let's just write that out here. And what we'll do is we'll compare it with our function here, P of t. So the template's going to be y, which is some population, equals a fraction with our a value in the numerator. So that's the carrying capacity. So again, if you remember the logistic function, it kind of has a shape that starts out exponential, but then it has an inflection point. And the carrying capacity is that kind of horizontal asymptote at the upper side of the function. And then in the denominator, what we'll have is 1 minus e to the power of negative k times time, all divided by what we would have as our c value. Again, that's coming out of solution of the differential equation. So I want to start just by comparing some items between the P of t that we've got and the template here. So to find my k value, I just want to locate it in the template. It is the power on e. And notice in the template, I've got a negative. So if I try to match the k up with my actual function here, I'm not going to highlight the negative because really the k value has to be positive. It's a positive growth rate. And that pretty much immediately gives me the k value. So it's 3/4, 0.75. A lot of times we would expect k to be between 0 and 1, but definitely positive. Moving along, when I go to find my carrying capacity, we've already mentioned where that is in the template. So it's in the numerator, it's a constant. So when I compare that here with P of t, definitely my carrying capacity is going to be 2,100. And just to remind that what that means is the kind of upper limit of the population growth is going to be 2,100. So those two items, really, we just identify the parts in the function. Starting with part C, though, I need to do some calculations. So I kind of mentioned already, initial population would be the population at t equals 0. So for me to find the initial population, what I want to do is just set up my function. So P of t, and in fact, I've already gone too far. I really want to calculate P at 0. So I'm just going to plug in 0 anytime I get to t. So 2,100 over 1 plus 29e to the power of negative 0.75 times, there's the t in the actual formula, 0. So it's really only going to affect that base e to the power. And when we think really it's going to be e to the power of 0, any base to the power of 0 is going to equal 1. So that whole exponential term there, really a factor down in the denominator, will go to 1. And so my initial population is going to be given by 2,100 over 1 plus 29. And when I divide that out, 2,100 divided by 30, in fact, we could probably just do that mentally. That's going to be 70. And that's our initial population. So you can kind of see the extremes here. We would start with an initial population of 70. It would grow very similarly to an exponential function, but then because this is logistic and the population is large, it'll have an inflection point and then it will never quite reach, but it'll get close to 2,100. Our last part for this first example is to find the time when the population is 50% carrying capacity. So for this example, for this part where I want to find the time when the population is 50% its carrying capacity, I really just need to think, what is half of my A value, which in this case is 2,100. That's definitely going to be 1,050. So that's what I want to substitute in for P of T. So I'm going to actually plug in the half value. So 1050 equals 2,100 over 1 plus 29 e to the power of negative 0.75 t. So for this part, I do have to solve for t. So it's a little more involved in the algebra, but not too bad. So let's just start solving. So what I'm going to do first is I'm going to multiply both sides by this denominator, 1 plus 29 e to the power of negative 0.75 t. So that's going to show up like so, 1050 times that denominator. By multiplying by this denominator on the right side, it's going to cancel what's there, and we'll just be left with 2,100. I want to then divide by 1050. It'll cancel on the left. Because of the way that we made 1050, it's really coming from the carrying capacity 2,100. That value is just going to be 2. So now I've got 1 plus 29 e to the negative 0.75 t equals 2. Subtract 1 from both sides. And in fact, let's go ahead and divide by 29. Got some funny notation there on the right, but I think we can kind of track it. So here on the left side, I've got just e to the negative 0.75 t equals 2 minus 1 is 1 over 29. I'm ready to pull that power down so that t is on the main level. So I'm going to apply the natural logarithm, and that'll do just that. It'll bring that power out front as a coefficient by my logarithm rules, and then I'll apply natural log on the right side. So almost to a time here, we've got negative 0.75 t. Natural logarithm of e is 1, so I won't write that even, equals the natural logarithm of 1/29th. And then to finalize solution for this part D, I would just divide by the coefficient negative 3/4. And that expression there, natural log of 1 over 29 divided by negative 3/4, that's going to be where my answer is. So I'm just going to take it to the calculator to get a decimal approximation. So here on Desmos, I am going to just type it in exactly as we wrote it. So natural log of 1 over 29, all divided by negative 0.75. And that's giving me a value here of about if I take it to the 1,000, 4.490. We'll take that back to the notes screen to finalize. So that time when the carrying capacity is at 50%, I'm sorry, when the population's at 50% of the carrying capacity will be 4.490. I don't know the units here. Could be years, could be days. It would depend on the situation, but 4.490 time units. All right, so our last task here is just to give the logistic differential equation that would, in a way, correspond with this initial function. So to do that, it's a lot easier than it seems. I just want to take the template for the differential equation. The template that we gave at the beginning really was a solution template for the logistic differential equation. Notice we called it a logistic function because it was solved for y. But when I'm looking for a logistic differential equation, I'm working from this template, dy dt. So you know it's a differential because it's got the derivatives on the y and the t. And the way that that's going to look, and again, this is given a lot of times before you would be given the actual logistic function. So it's a template that's pre-established. So dy dt equals k times y. So same growth k, y times 1 minus y divided by carrying capacity a. And again, that's established. So all I have to do is, in a way, reverse substitute back in k value and a value, and then I've got my differential equation. Pretty simple to do. So let's just fill in here. So I got dy dt, and in fact, since we're dealing with this variable p for population, I'm going to call it dp dt equals, so my k value, that notice we kind of found these parts in our first tasks, is going to be 0.75 y times parentheses 1 minus y divided by my carrying capacity 2,100. And really with those two substitutions, that is complete. So I'll box that. Again, let me box these five answers that we found. So we got differential equation, we got the time when the population's at 50% carrying capacity, initial population 70, carrying capacity is 2,100, and the growth rate is 3/4. So this example starts with a logistic function and ends with the differential equation that corresponds to it. Let's take a look at a second example where we really look at the reverse situation. I'm starting here with the differential equation. So here we've got dp dt. I see I've got one thing I need to fix here. This should be 0.3. Let me just correct that here at the outset. dp dt equals 0.3 p times 1 minus p over 100. So we've just looked at that template. So let's just bring it again. dy dt equals ky times 1 minus p over a. In fact, I'm mixing them up. This should be in this version y over a. So again, that's the thing we just wrote for the previous example, and we're starting with that here. So I want to find three things: k, the carrying capacity, and the value of p at which growth rate is greatest. So let's start with the pieces that are easy to identify. K, again, in my template, is a coefficient on the population, or my y value or my p value. So here it's going to be 0.3. We'll fill that in. So our growth rate here is a little less than the first one, 0.3. Same deal with my carrying capacity. I just want to identify where it should be. So it's in the denominator under the population. Carrying capacity here is 100. The third part here is a little different. We're looking for the value of p at which the growth rate is the greatest. So like we did in the first question, I just want to consider the way that this logistic function works. Again, it starts as an exponential function, which is concave up. And as you can definitely tell, like the growth gets higher and higher as we go. You can think the slopes of the tangent lines get more and more steep up till this point at which the function switches concavity. So just thinking about function analysis, if I go from concave up to concave down, do you remember the name of that point where that changes? That definitely good has to be the inflection point. So just kind of by an informal analysis of the function, the growth rate is going to be greatest at the inflection point, because that's where the slope of the tangent lines is the most steep. or have the greatest value. Because at that point, if we let it keep going into that blue part of the logistic function, the growth rate slows down. It's concave down. So algebraically, in fact, in terms of calculus, we need to think, how do I find the population where that p-value, or I'm sorry, where that growth is at the greatest? How do I find that? Well, we would take the second derivative. So if I've got the function here, or I'm sorry, the differential equation here, it's already the first derivative of the original function. So all I need to do is take the second derivative, which is just take the derivative of the differential equation. So let's do that. So we're working on dp dt equals 0.3p. Now, one thing I'm going to do to help out with doing this differentiation is I'm going to distribute that term 0.3p through the parentheses. So that's going to be 0.3p minus 0.03. I'm going to wrap that up with the denominator 100, and then it's p times p, so p squared. And then I just want to differentiate on both sides. So I'm going to write ddt here. We'll use the Leibniz notation, and ddt here on the right side. So now what I've got here on the left is the second derivative. So second derivative of p with regard to t is going to be equal to, so I'm going to just take derivative of these two terms. So 0.3p, its derivative is going to be just the coefficient 0.3 minus 0.03 over 100 times 2, and then p to the power of 2 minus 1, or just p to the first power. Now that's a good equation. Now what I want to do, recall, to find the value at which we've got this inflection point, I'm going to take that second derivative, set it equal to 0. Again, on a second derivatives graph, you'd see that change of inflection, or concavity, I'm sorry. The change from concave up to concave down would be where that function is, where the second derivative is going from a positive value crossing the x-axis to a negative value. So definitely that point is going to be where it equals 0. So let's just solve now for this p-value. So I'm going to start off here. Let's subtract 0.3 from both sides. And that gives us kind of an opportunity to wrap up this coefficient here on the variable. So I'm going to multiply 0.03 times 2, that's 0.06 over 100p equals negative 0.3. And then I want to divide both sides by, I'm going to put this as a decimal, 0.0006. And I'm going to divide that on both sides. And at that point, I've got a solution here. So p equals, so my negative signs are going to cancel, 0.3 divided by 0.0006. And all I need to do at this point is take that to the calculator. I think I've got an error here. I've got too many zeros. So let's fix it before we go to the calculator. It should be just 0.3 over 100. So not quite sure how I managed to smuggle in an extra 0, but let's write that wrong. So what that'll do is that'll just be the thousandth. Okay, so that's ready for the calculator. So again, just got to adjust that. So we're looking for 0.3 divided by 6 thousandths. Let me head over to Desmos just to calculate that. In fact, we could probably calculate that right here on this screen. So we'll do so. 0.3 divided by 0.006. And that's going to give me this value of 50. One thing I notice is that that's half the carrying capacity. So it is a good pattern to notice there. Thank you for joining for this investigation of analyzing a logistic function and then taking a look at kind of the reverse picture, analyzing a differential equation for the logistic function. See you soon.